give a little bit more time for those who have just come in. Once again, one more thing, just wanted to check, who here has experience running IPython notebooks? Please raise your hand. Just want to make sure you're distributed throughout the room. If not, so it looks like there's this patch over here that there's a lack of experience. So I was wondering if some of you might be able to swap with someone who has, if that's possible. Oh, bummer. All right, and final check. How many of you had dictionary for S? Raise your hands, please. Okay, and how many of you had a list for my favorite things? Okay, great. It's supposed to be pretty trivial, so if you got those. If you didn't get it, but you had some other plausible data structure, I mean, list and dictionary are probably the most obvious, but there are probably other things that work too. All right, so for those who just came in, find out from your neighbor where to get the repo and everything, and try to get into your environment as soon as possible. Just a few administrative matters before we get started. PyCon loves data, and they're asking for evaluations. And so I've provided the link on the GitHub repo README file as well. So if you go back to the README file, or if you go to the online repo, you'll find a link to the evaluation form. And I'm going to leave about 5 minutes at the end for you all to fill that out. One other minor administrative matter is that I've been struck by a stomach bug over the past 2 days. So if during the middle of an exercise, you suddenly see me walk out of the room, it's because I have an urgent need to go to the restroom. Please keep calm and carry on with the exercises as we go along. I'm just going to put that out there straight up front. But I promise not to be gone for more than 5 minutes at a time. All right. How about we get started? Is everybody feeling good with that? Yes, yes, no, yes, thumbs up, thumbs down. Cool, great, great, great. All right. So today I'm going to share with you guys some stuff about network analysis. Now I just wanted to get a real quick check, background check. How many of you have taken some computer science class that dealt with, say, graph theory or networks? Okay. How many of you have actually implemented algorithms for network analysis? All right. So for those of you who've got experience with that, some of this stuff may not be new, but for the rest of you, we are going to actually spend a lot of hands-on time trying to implement things to understand networks. So earlier on, I've asked you guys to pair up. Now I'd also like you guys to do one other thing. PyCon has provided these mini business cards, and they should come with your badges. So I'd like you to take out two of those badges or two of those mini business cards. And on the back of them, there's some things I'd like you to write. Now, if you need a pen, I have 3 extras here. Just raise your hand if you need it. Okay, first come, first serve.
Are regular size cards?
Regular size cards work too.
I didn't register yet for the site that sent me upstairs. So I'm gonna
That's okay. I've got some extra blanks. On the back of one of these cards, pardon me? Okay, if you guys could help out a little bit, there should be some blanks. Those blanks work as well. All right, please share them around. All right. On the back of one of those cards, I want you to look around, right? Look around the room and write down the names of people who you can name. And if you don't know anybody, you at least know one person in this room, and he's standing at the front of the room. All right, once you're done with that, on the second rear side of the business, on the second business card, on that rear side, I want you to write down a list of cities that you've been to within the past year, and I want you to write down those names only if and only if you have been out of the port of disembarkation for more than 1 hour. So if you arrived so for example, on my way from Boston to Montreal, we stopped at Burlington, but I didn't get off the bus. So technically, I've never been to Burlington. Past 1 year. Change it from 2 to 1 year. So on the second business card, on the back of it, can you write that down as well, please? Okay, so the second question is, can you write down a list of cities that you've been to for which you've gone past the port of disembarkation for more than 1 hour? So my example was the negative example. I never left the bus on the way when we stopped at Burlington, Vermont, so I've never been to Burlington. On the other hand, I've been in San Francisco because I've exited the airport, taken the shuttle to the city downtown part of the city. All right, are we all done with that? Thumbs up, thumbs down. All good? If you're done, please keep your thumbs up. All right, that way I can get a good gauge for how people are doing, how the class is doing. All right. It looks like most people are done. All right. So those questions, the answers that you've written to those questions will come in handy later on. The list of names will feature early on, and the list of cities will feature later. But meanwhile, let's get back to networks. So networks are also known as graphs. In the mathematical CS world, networks and graphs are terms that are interchangeable. Networks are useful for understanding relational problems, right? And so in most of our common experiences, we're used to dealing with entities. So I'll talk about how many people are in the room. But we rarely focus on the relationships between the entities. And so that means the relationships between people in the room. And so networks are an incredibly useful way to understand relationships between entities. So networks are comprised of two things, or graphs are comprised of two things. There are the nodes, which represent the entities, and then there are the edges, which represent the relationships, however we've defined them. So just to get through some basic terminology here, nodes and edges are what comprise a network. And in a network, if two people or two nodes are connected to each other, they are neighbors of one another. Also, there are generally two types of networks that we can talk about. So one is an undirected network, and this is the case where the edges don't have a directionality to them. And the other case is a directed network, and this is the case where the edges represent some form of directional relationship. All right? So some examples of networks include, say, for example, our social network platforms, right? Facebook, LinkedIn, and Twitter. And we can represent users as nodes, and whether two people are connected by a relationship as the edges. Some other examples of networks include, for example, air traffic networks, right? And we've got directed edges between them, which indicate whether two airports are connected by flights. And in this case, there is a directionality that is associated with it, right? You might, if you're in the finance world, you might want to talk about stock market correlation networks, right? And this happens when two stock prices are highly correlated with one another. You can start to say, let's have a cutoff score and represent this data, this stock market pricing data, as a correlation network. And if things are highly correlated, then they are joined by an edge. I'm a biologist, or rather I'm a bioengineer. So for me, I like to talk about interacting molecules, proteins or protein DNA interactions, or at some, or even at some more granular level, interactions between atoms in a protein. And we can represent this data, again, as a form of a network. So when we talk about networks, the key questions that I'm hoping to answer today are, how do we model a problem as a network? And how do we extract useful information from a network? And how do we look for interesting things about the network's structure? So by the end of this tutorial, I'm hoping that you will be able to use the NetworkX package in the IPython environment, that you'll be able to model your data, whatever data you might end up with using nodes and edges, that you'd be able to compute network statistics, and finally that you'd be able to have some basic feel for how to visualize networks and stuff. I could. Alternatively, you can open up the preface notebook as well. All right, and I just wanted to give before I continue, I wanted to give a few credits. Firstly, a shout out to the PyCon rehearsal class back in Boston for providing feedback on the material, as well as one undergrad student in our lab who helped with a few of the algorithms and implementation of some of the visualization tools that we'll be using here. All right, so because this tutorial is going to use NetworkX heavily, the first thing I want to make sure everybody is capable of doing is using NetworkX. And so if you could all please open up notebook number 2. Notebook number 2 is the NetworkX Basics. So everybody got that open? The notebooks are on the GitHub repository. Please find out where they are from your neighbor. Okay, so in this tutorial, there are two versions of the notebooks. There's the instructor version, which I call the cheat version, and there's the student version, which is what I'm hoping you will work with. If you get stuck on an exercise, feel free to open up the instructor version and look at the answer. But for the most part, I'm hoping you will stick with the student versions of the notebooks. All right, so NetworkX is, yes, sorry. Pardon me? That shouldn't be necessary. If you go to the GitHub URL directly and you download the zip file, no usernames are required. All right. Are there any other problems so far before we continue? All right, if there are none, let's move on. So, in NetworkX, a graph is represented using dictionaries. The nodes are one dictionary in the NetworkX graph object, and the edges are a dictionary of dictionaries in the NetworkX object. And so what we're going to do is we're going to run through a very simple synthetic social network example that I created just to help you get a feel for how to use the NetworkX package. So if you scroll down here and you look at this particular cell, you will be able to load in a synthetic social network that I created. And this synthetic social network is essentially a random graph which has individuals as numbers and whether those two people are friends by the edges. So if you run that cell, you should get a drawing of the network at the bottom. All right? Everybody cool with that? Now, if you run this cell multiple times, you will notice the layout of the drawing will change from time to time, and that's because the layout algorithm for drawing networks is randomized. And so the exact placement of nodes and edges will be different. However, the data underlying the data is still the same. All right? So let's first try to get a feel for this network. And as I mentioned earlier, in the process, we'll get to learn how to use the NetworkX package. So if you scroll down here, and if you run that cell, you'll see that you can call on a list of nodes that are present inside the network. All right? And if you run this code as it is, what's returned is a list object, and all of the nodes are the entities inside that list. If you change it to data equals true, so if you'd like to add that little bit on, and you run the cell, you will see that there's additional metadata that will display. All right? And in this case now, it's not a list of integers or a list of strings for that matter. It's a list of tuples in which each tuple corresponds to one node. And in the first element of the tuple, it is the node name. And in the second element of the tuple, it's a dictionary of node attributes. So we have the biological sex and the age, which I just sort of made up and flipped a coin. All right? Everybody cool with that? So let's move on. So as a very, very quick exercise, can you write one line of code that returns the number of individuals represented inside the graph? And when you're done, please give me a thumbs up. Okay, this should be fast. Yes? Ooh. I am not so sure about this then, this one. I would suggest, yeah, I'm not so sure actually how to fix this one. This is the first one. Right. Right. Is everybody cool with this one? It should have been a length of g dot nodes, right? So the next thing, right? Is everybody cool with this one? All right. The next thing you can do is you can query the network for a list of edges. And the function call is g.edges. And if you run that cell, you should see a list like this. In the list, each element is a tuple. And the first element and the second element of each tuple are the nodes that are connected to each other by an edge. If you run, similarly, data equals true in this cell, you will see a date field which comprises of, you'll see the edge attribute dictionary show up. And in this synthetic social network that I've created, there's a date field that says when this friendship, so to speak, was formed, right? And so the main point about this earlier part here is that you can actually store metadata associated with the nodes and metadata associated with the edges. So once again, trivial exercise, write a single line of code that returns the number of relationships or the number of edges present inside the graph. And once you're done, please give me a thumbs up. Okay, okay, good. Good, good, good. Are most of you all done? If you just very quickly give me a thumbs up. Okay. So once again, it should have been length of g dot edges, right? And so that's how we look at that. All right, so looks like I've already gone through data equals true, so we can skip that. If you could go down to the exercise over there, can you count how many males and females are represented inside the graph? So take a few minutes to use that, to check that out. How's everybody doing here? Okay. If you're done, please give me a thumbs up so I can just really quickly see. Okay. All right. We'll give it one more minute on this problem. Okay, so my suggested solution is to use a counter object. And one of the things so those of you who came in early, I asked you about how comfortable you are with list comprehensions. And part of the reason is because a lot of these basic network queries can be expressed in this very compact form. Right, so if you got something like 15 and 15, you are on the right track. If not, no worries, go check the instructor notebooks. All right, so we've also gone through storing attributes in the attribute dictionary. So I'm going to ask you to now do the next exercise, which is given the data, given the edge data that was that's present, can you figure out the earliest date and the last date that these relationships in this synthetic social network were formed? And try to use a list comprehension if possible. But if you can't, no worries too. Let's get the timer going. If you're done early, you might want to see if others might need a bit of help or not. Are you still having Matplotlib issues?
Basically, I tried to uninstall Matplotlib and
Okay.
basically,
Okay. I'd suggest maybe pair coding with someone else just for the rest of today.
sounds good.
Yeah, the notebooks are available online, so you can always download them anytime. Yeah. Yes. You're using Python 2.7.
Yeah,
Okay, so
it's a Python.
there's a Python 2.7.pkl there. Yes.
Well, so I'm way back. I'm still trying to install NetworkX and all that.
Okay.
Because I was trying to do the tutorial. Anyways, it's telling me I don't have Matplotlib. I just tried installing it. Is there any specific place I should get it from?
Python version that you're using. So
Oh, okay.
if it's not associated with Canopy, then it's not going to work. This is Canopy, right?
Yeah.
Yeah, if it's not associated with Canopy, it's not going to
I'm
work.
just doing this in a command line, and
Okay.
I tried to pip install it, and it still didn't work.
So you might be using System Python. If you can't catch up for this one, I'd suggest maybe pair coding with someone else just for the tutorial,
Okay.
because the notebooks are going to be available online anyways,
Okay.
so you can download them later. Quick show of thumbs, how many of you are done? Okay, we'll give it 1 more minute. Actually, you can follow along on the instructor notebooks
Yeah,
too.
I was just
Okay, cool. That works. Okay, quick check, how are you doing? If you're done, just give me your thumb one more time. All right. Okay. So once again, my proposed solution, if you look at the instructor notebook, is a list comprehension. And so it's a few steps, get the list of dates and then calculate the minimum and the maximum from that. All right? So the next exercise that I want you to try out is to add nodes to the graph and add edges to the graph. So if you click on the URL that's provided, you'll get to see a link to the official NetworkX tutorial. And so essentially what I'm doing here is giving you the shortened version of it. And I'd like you to follow the coding pattern for adding nodes and adding edges, given the data that's inside the question prompt there. It looks like there's a grammatical error in my notebooks, which I will change. How's everybody doing? Okay. You would pass in, so I'm not going to belabor this one too long. My answer is displayed here, and that's essentially the coding pattern that you would want to go for. So let me just zoom in a little bit. All right, so to pass in the attributes dictionary, or to pass in the attributes, you can simply put the attribute, the non-string version of the attribute equals something. And so for example, age equal 22. And if you query back the graph, and I'm going to, let me see if I think I've already run all of these things. So I can try to prove to you that the data will come out as necessary. So if I query node 31's attribute dictionary, the attribute dictionary will come out as expected. So this one I don't want to belabor for too long, because we're going to use the name knowledge data that you all have written on the back of your mini PyCon business cards. All right? So if you're not done with this one, that's okay. Don't worry too much about it. So we're going to go into the next mini portion, which is how do you visualize network data? And there are multiple strategies for doing it. And I'm going to use a live exercise to illustrate a few things. One, how do you construct a network from scratch? Two, how do you use different libraries for, or different utilities for visualizing the network? So I'm going to pretend today that you are all a list, elements in a list. All right? And we're going to go in snake-like fashion from this side here, first row, all the way to the back. All right? And so what I'm going to ask you to do is, as I go along, I'm going to ask you to shout out your name and your nationality. So how many of you are Canadians? I'm a Canadian, thankfully. How many of you from the States? Americans. And how many of you are not from either? Great, this is perfect. Because this will get us to a really nice way of visualizing data, network data, which is on hive plots. All right, so as I go along, so this might take a little while, so bear with me. You can actually also try to code along with me for this exercise, all right? So we're going to iterate over this long list, snake-like list of class participants. And this will also maybe hopefully help me to get to know your names a little bit better. So, but I'd like you to, as we go along, shout out your name, shout out your nationality, and give me the names of people who you know in the class. All right? All right, so let's start from over here. Paul from Canada. And how many names do you know? All right, you know yourself. All right, that's like a self-edge. All right, next up.
Max US.
Max US. All right, and how many names do you know? Martin. Okay. Max and Paul. All right. Next up. Okay. If you don't mind, those of you who are not from US or Canada, I'm going to use the grouping other. Okay. And Martin. Okay. Oh, finally someone knows me. All right, next up. Okay, Jim. US. Pardon me? Federico. All right. Next up. Lucas. And Lucas, who do you know? All right. Next up, Thomas. US. All right. That's this. It's this thing called homophily. People who likely know each other likely have similar attributes. So I guessed you were from the United States as well. All right. And Thomas, who do you know? You know Lucas. All right. Next up, Brad. You're from the US. All right. Yay, someone knows me too. I should probably add myself. Otherwise, I'll come up with a blank attribute. Next up, Troy. Troy, is that right? All right. And who do you know? Okay. Next up. Corey, did I write your name correctly? It's O-R-Y, not O-R-E-Y. Okay. What's your nationality? Canada, right? Homophily at play right there. All right, next up. How do I spell your name again? Gokhan. Okay. You know Max. Okay, next up behind. R-I-L-E-Y. All right. From the United States. You know Zach. Riley, Zach. So, all right. Who's next? Steve, US. And Steve, who do you know? Okay. Whoops. Moving on. Okay. And Ryan, who do you know? All right. Next up. Andrew from the US. All right. Oopsies. All right, next up. R-O-N-A-N. All right. You know, sorry. How do I see? Cody. Yes, okay. Sorry, just give me a moment. And so, Cody. Okay. Okay. All right, next up. John, J-O-H-N? John, okay. John, you know, sorry, William, me, and, oh, the other. Okay, I'm going to call you Eric too. Okay. So that's actually a good point. nodes have to have unique names, and I think that's a good thing because this is all represented in dictionaries, and dictionaries can only have unique keys. All right. So Eric 2. U.S. Okay, going on. William. All right. Going on.
Hi, I'm Tom from New Zealand, and I don't think I know anybody here.
Okay.
Even you, because I came in a few minutes late and missed the introductions.
Okay, not a problem. Actually, I didn't even introduce myself, so not to worry.
Sorry, from New Zealand.
My bad. So you know yourself then, Tom. All right, moving on.
I'm Chris from the U.S.
CHRIS.
Yep.
Okay.
And I know Eric and Stu.
And you mean Eric 1 or Eric 2?
Eric 1.
Okay. Stu, S-T-U. All right.
I'm Stu. I'm from the U.S.
All right.
I know Chris, you, and Zach.
Okay. Okay, moving on.
Jack from the U.S. And I know Riley, Stu, and
So Zach, you know Stu. Who else do you know again? Sorry? Riley. Clint. All right. Who's next? Clint from Canada. Okay. Okay, moving on.
Aaron from the U.S.
AARON. All right.
Eric 1.
My apologies, I didn't catch that one again.
V-I-S-H-A-L.
VI
S as in Sam, H-A-L as in Larry.
Vishal. Okay.
And that's me.
All right, so Vishal
Vishal
from
from the U.S.
the US.
And I know Eric 1 and Aaron.
All right.
And myself.
Okay. Oops, sorry, Vishal. Okay, I'm going to temporarily pause at this list, seeing as how big the class is. So if I didn't get to you, we can make this graph later on. So who's after Vishal? Cole? Okay, Cole onwards. If we get time at the break, we will continue to make this class graph, all right? So what I've done here is I've created and initialized directed graph, so that's the digraph object. And the reason I've chosen the directed graph is because this network that we're creating is a name knowledge network. And so if I know your name, but you don't know my name, then the relationship that we have is a directed fashion, right? What we're going to do is we're going to look at, try to find a way to visualize this in a rational fashion. Now, we could use the traditional node link diagram, but that's sort of, as the number of nodes grows, it rapidly becomes less a node link diagram and more a hairball, right? And you don't want to look at hairballs. They're very uninformative. And so Martin Kurzwinski at the BC Genome Science Center, that's my home province, he's actually created 2 ways of visualizing data called circos plots and hive plots. And I'm going to show this to you guys. I'm going to show hive plots with the live class graph. I'm going to show alternate versions of graph visualization using the synthetic social network. All right? So because nobody's implemented hive plots for Python users, I went and did it. And so that's part of one of the things I've asked you guys to install. And the way that we use it is we create this grouping, we create this group of dictionaries that are passed in to the graph. So if you could just give me a few moments here. So we're going to create a Canadians group, or Canada group, a US group. Actually, you can copy all of that and just change the criteria. If we had different types of edges, we would have said, some edges were of this category and some edges were of that category. We could actually group the edges as well, but we're not going to do that in this case here. The final part is to set the color of the nodes. And I think that should work. Oh, something went wrong. Did I spell nationality wrong at some point? Jim. Pardon me? Ah, thank you. That happens sometimes. Now, I think there are some individuals for which they don't have... Let me just very quickly introspect this graph. So split the cell, g.pt.nodes, data equals true. Federico, what is your nationality? Argentina. So I'm going to have to add you as a node. And I think that's... Pardon me? Federico. Thank you. All right. And what's the... Thank you. Group 1, edges, CMap. Oh. One last little piece. My apologies. I noticed that there was an issue with that hive plot package, but I forgot to update it on my own system. Irony of ironies. Oh. Okay. Never mind. That's a little embarrassing. There's this inconsistent use of tabs and spaces in the indentation, which is a problem with the package that I wrote. But I'm going to very quickly describe hive plots in abstract. Imagine if you had a 3-axis plot, and you had one axis representing all of the US people, and then another axis representing all of the Canadians, and a third axis representing all of the people who are non-American and non-Canadians. At one glance, immediately you can tell how many Americans, how many Canadians and how many non-American and Canadians there are. The next thing you can do is you can also check to see within a group, so if you split this US group, for example, and you split it into two, you copied it and duplicated the axis, you can immediately see between the US people, how many people know each other. And then you can also see edges drawn between the US-Canada axes. And you can see, effectively, you can see how many intra-group and inter-group connections there are. So over the break, when we take the break, I'm going to try to fix this problem, and I'll try to get back to it so that you guys can take a look at it. So in the meantime, though, I wanted to bring you down to the bottom part of the graph here, of the notebook here, which is on how you draw and represent networks. So hive plots sort of failed. Not to worry, I will get that fixed by the end of this class. In the meantime, if you take a look at the stuff below and you run the cells over there, you'll see the traditional node link diagram, which with NetworkX you can actually also add in the node labels if they're small enough to fit inside the nodes. Now, like I mentioned, this very quickly devolves into hairballs, and you don't want to use this beyond, say, 20, 30 nodes. So an alternate way of looking at graphs is to use a matrix. And you can use a heat map. Well, actually, graphs can be represented as a matrix. And in this matrix, what you would have is you'd have all of the nodes lined up on the x-axis, and all of the nodes again lined up on the y-axis. And if the edges are if the two nodes are connected by an edge, you'd add a 1 to that cell, right? And so you can then actually visualize the adjacency matrix as a heat map. Now, if you had variable weights assigned to the edges, right? So now we're not talking simply whether I know you, but how well I know you. And if I could represent that by a number, I could go from 0 to 1 or 0 to 100, and then represent that by a graded heat map. If we take a look at the third visualization at the bottom, this is what I meant by a Circos plot. So with the Circos plot, what happens here is you actually can see very quickly. So if we order all of the nodes in order from the 12 o'clock position all the way to the other side, and we draw edges over here between the two nodes, you can immediately see, for example, this node over here has no edges into it. This guy over here also has no edges associated with it. And so these are the lonely people in the social network, right? And there are some nodes, like number 19, if I remember correctly, that have a whole ton of connections to other people, and these are highly connected individuals in the network. All right? So with that, that's going to end the first notebook on the basics of NetworkX and how you do some basic visualization. And as I promised, I will go and fix up the code such that we can actually take a look at this partial class graph that we attempted to create. In the meantime, I'd like you guys to now open up notebook number 3. And notebook number 3 is a notebook that discusses, in which I would like to try to run through an example of hubs, or an example of how we interrogate the structure of a network. All right? How do we find out what entities in the network are very important? And how do we identify whether we can get from one place in the network to another place in the network? All right? So now, I noticed some of you had issues with the Python 2.7 pickling issue. So if you run this top cell over here, but you're running Python 2.7, add a 2.7 to the end of the file name, and you'll get the pickled social network loaded up correctly. All right? All right. So within a social network, there are people who are well known. And if more people in the class had called out my name as we were going through the class list, then I would have been a very well-known individual in the class. So one way that we can figure out how important an individual is to see how many neighbors that individual has, all right? So if you remember the definition of a neighbor, two nodes are neighboring each other if they are connected by an edge. So NetworkX lets us figure out the number of people that an individual is connected to. So you run the cell below, and you say g.neighbors for node 7, you can actually find that number 7 is connected to number 24 and 25, and you change that to number 9, you'll see that individual number 9 is connected to 24, 17, and 11. All right? So what I'd like you to try to do is, another thing that you should notice is that g.neighbors returns a list of nodes. So I'd like you to try out this exercise where you create a ranked list of the importance of every individual inside the network. All right? And the key here is if you use the neighbors function, you should be able to figure out how many people any given individual is connected to. Yes. Yes, there is. In NetworkX, it would be called successors and predecessors, right? But we're not going to use that today, but you can always look that up. Yes, Martin.
Previous example, what goes into edges? I mean, how do you define groups of edges? What are those? Because I got the graph working, but not the edges.
I might have forgotten to do that, but that's exactly what we were looking for. That's right. That's right.
And there are things.
There will be stuff going through there. For edges, if you want to try that, what you can do is do source sync, like tuple source sync follow the coding pattern that I've highlighted below for iterating over edges using list comprehensions.
Okay.
And you can get a list of edges put into that.
A group of edges would be
Edges that have similar attributes in their attribute dictionary. But for this particular case, it's not necessary. So if you follow the hints in the notebook, one suggested output would be a list of tuples. The first element in the tuple is the node ID. Second element is a list of its neighbors, and you can sort by the length of its list of neighbors. Okay, I see thumbs. I see thumbs. Great, great, great. Thank you. We'll give it, say, another 2 minutes. And if you're not done, not to worry. Like I mentioned, feel free to open up the instructor notebook and take a look at a suggested answer. So if you're not done with this exercise, again, no worries. This one was a bit more challenging when I ran it through the rehearsal class. Essentially, the idea is we create a list of tuples, g dot with n and g dot neighbors of n, for every node inside the graph, and we sort it by the length of the element number 1, so not element 0, but element 1, the second element inside each tuple. And in this case, I said reverse equals true so that I could get it from most highly ranked to least highly ranked. All right? So the number of neighbors that an individual has is intimately tied to this metric called degree centrality. So degree centrality is a metric that says how connected is a particular node to other nodes inside the network. And essentially the definition is, the mathematical definition is the number of neighbors that a node has divided by the total number of nodes that are present inside the network. So if you take a look at and you run the cell below, you do nx.degree centrality g, you will see that number 19 has, say, the highest, and as was with the case, as we saw with the visualization earlier, individual number 5 and individual 18 are not connected to anybody, and so their degree centrality is actually 0, right, by definition. So so what I want you to try out now is to create a histogram. So using matplotlib, if you're familiar with this, might actually require more than individual coding. So if you want to pair up or you want to group up, feel free to do so. But can you create a histogram of the distribution of degree centralities and a histogram of the distribution of the number of neighbors that an individual has? And the third thing that I'd like you to do is to create a scatter plot of degree centrality against number of neighbors. And once again, this is about the network statistics and how do you visualize basic network stats. You can also ignore the times that I had provided. They didn't work in the rehearsal class, so I'm just going to ignore them here. And I'm actually going to delete them live. Feel free to talk with your neighbors, physical neighbors, not graph neighbors. Although I did notice that the graph neighbors are usually the physical neighbors as well, which is a very cool thing. So that to get item number 1, to get to the plot for number 1, you only need to have a list of degree centrality values. For number 2, you only need to have a list of number of neighbors. So don't complicate the problem beyond that. So just want to see a show of thumbs. How many of you are done with number 1? Okay, so number 2 should be analogous. And how many of you have at least attempted number 3? Show of hands. Okay, we'll let it run for a little bit more as well. Yes.
Sorry, right at the beginning, but I get this.
This is Python 2.7. So at the end of synthetic social network, add 2.7. So before the .pkl, add a space 2.7.
Okay.
Yes. Did you get that?
Well, I'm seeing this, but
That is correct.
for both the centralities and the neighbor.
Yes,
Because
that is
it's-
correct. That's correct. So if you're not done with number 3, that is okay. As long as you got a chance to see for yourself degree centrality and number of neighbors, those distributions are identical. Essentially, you should see a scatter plot which you can draw a perfect straight line through the dots. And this stems from the mathematical definition of degree centrality, which is number of neighbors divided by total, simply normalized to the number of nodes. All right? Now, I just want to quickly poll everybody on question number 4. If I have n nodes, how many possible edges are there in total, assuming self-edges are allowed? In an undirected graph, sorry. In an undirected graph. Not n factorial, but
n plus n minus 1 plus n minus 2, then like if there was 5, it would be 5 plus 4 plus 1 plus 2.
and choose to. That's the answer to the second part. So if self-edges are not allowed, in an undirected graph, you'll have n times n minus 1 divided by 2 because it's undirected. And if self-edges are allowed, then it's n square, all right? So this is one property of networks that you might want to commit to memory because it comes in handy when you're doing sanity checks on your on your graphs, right? If you have n edges and n nodes and you end up with more than n square edges, you've either created a graph which allows multiple edges between two nodes, or your graph is wrong. So that's something useful to keep in mind. All right, so the next thing we're going to do prior to the break is we're going to look through paths in a network, all right? So let's think about the example in this synthetic social network. If we wanted to pass a message from individuals to from one individual to every other individual in the network, we can ask, what is the minimum number of people we need to pass the message to, in such that in the long run, if the message is passed, one per day, etc., eventually everybody in the network gets the message. And so it's therefore becomes important to understand whether people are connected by by a path from one individual to the next individual. So if we take a look at this graph over here, intuitively, if you remember, 18 and 5 were the individuals who were not connected to anything else, but the rest of the individuals were. And so what would be the answer to the minimum number of individuals that we need to pass the message to? Be 3, right? We'd have to pass to anyone who's connected in this big massive network, and then we'd have to pass it to individual 18, and we'd have to pass the message to individual 5, such that if one person in this bigger network were to start passing the message on, eventually everybody would get the message. But 18 and 5 are not connected by any path to any other individual in the network, and so therefore they need to have the messages passed to them individually. Two pointing outwards in the middle.
Outward pointing edges from one node in the middle, and it's still, you can't access the full network.
Not in this example. In this example, 5 and 18 are disconnected from the network.
Okay, so it's not a directed graph.
It's not a directed graph. This is an undirected graph. All right? So another problem that we can try to look for is to say, what's the shortest path between two nodes, right? So for example, if we wanted a message to go from individual number 19 to individual 24, what's the shortest number of hops needed to take for the message to be passed on? And this has actually a lot of applications in wireless communications, mesh networks, etc. But we're not going to try to solve their problems. We're trying to try today to look at the basic version of the problem. How do you find out what the shortest path is between these two nodes? So what we can do is we can do what they call a breadth-first search. And it's essentially a greedy way of doing it. So for example, if I wanted to pass the message out, I can then begin with a queue of nodes, which is myself. And then I can start to ask, who's my neighbors? Over all of my neighbors. Is the destination node present inside, is the destination node present in my list of neighbors? If it's not, I'm going to have to go to each of my neighbors and ask who are their neighbors and see whether the destination node is present. And so we keep recursively iterating until we actually find the node, the destination node that we're looking for. And so what I'm going to have you guys try is to implement this logic. This is a challenging problem, so be forewarned. If you don't get to the final solution, it's perfectly okay. But I would like you guys to at least give it a shot. Give it a shot to see if you can implement an algorithm called PathExists, which takes in two nodes and the graph of interest and the graph that they belong to, and returns a true or false that indicates whether a path exists between those nodes. And if you want to group up and discuss this and have one person be the main coder, that is perfectly fine as well, because I understand this one is one of the more challenging problems in this tutorial. And because this problem is challenging, if you need to get up and take a break, this would be the perfect time to do so as well. Like if you need to go for a walk, clear your mind, please by all means do so. Or if you have an urgent need to go to the restroom as well. So how are people doing with this problem? If you're done, okay. So this admittedly is one of the more challenging ones. If you want to get a lift up on that, leg up on that, you can open up the instructor notebook and take a look at one of a suggested solution. And I'm just showing my version of the code in case you want to look at it or reference it. It's a bit more verbose. There are a few more statements that are added, for example. All right, so I'm gonna stop the timer on this one, and as I was saying, that's the pseudocode is written up there. All right, so if you didn't complete this challenging problem, that's totally okay. This actually took me about half an hour's worth of time to thoroughly flesh out in a slightly more compact piece of code. So I went through many iterations to be able to do it. But really the main concept is if you want to be able to search for whether a path exists between two nodes, one possible way of doing it is a breadth first search, right? And you iterate it over. It's like iterating through onion layers, right? You start from the core, you go to 1 layer out, 2 layers out, 3 layers out until you find your destination node. And that's really the main concept I wanted to show. This will also be the last exercise where I ask you to implement something that NetworkX has already implemented. All right, so there will be no other problems like this one. This was just a challenge problem. But if you look at nx.hasPath and you pass in the graph and you pass in the 2 nodes, then you should be able to get a true-false on whether 2 nodes are connected by a path. All right, now at this point, I'm going to have the class break, take a break for 10 minutes, go and refresh yourselves. And if you have any questions about the material so far, I'm also happy to try to answer them over here. And I think there are refreshments provided outside or something. So please go ahead, stand up, take a break, stretch, all that good stuff. All right, so as I mentioned earlier, my apologies. Let me just get this going back up. And let's put this back up here. Okie dokie. So as I mentioned, that last algorithm I tried to have you implement is the only algorithm that we'll try for this class, which NetworkX has already implemented. So we're not going to do any more problems of a similar type. So as mentioned earlier, NetworkX has a hasPath function that you can do, that you can use. You can also use the shortest path method that identifies one of the many shortest paths that are available between two nodes. So an example here is to go from node 4 to node 14. One has to, if a message were to be passed from node 4 to node 14, one of the shortest paths available is through node 19 and node 17. All right? And so what we're going to do at this point is we're going to build on the NetworkX API, and we're going to try to see if we can build graph query functions that use the NetworkX, use what has already been implemented for us, but to do some higher level searches. All right? So what I'm going to ask you guys to try is to write a function that extracts the edges in the shortest path between those two nodes and draws it to screen, all right? And one hint that I'll give for you to try this out is if you take this list of nodes and you pass it into g.subgraph, you'll actually get back a new graph object of the same type as the original graph G, well, basically over here. And then you can draw the graph to screen, right? So please give this a shot. And once again, ignore the timing on that one. If you're feeling stuck, again, feel free to open up the instructor notebook and take a look at the answer, or one possible answer. If you're done, can I have a show of thumbs? All right. Okay, we'll give it say another minute and a half or so. So if you test your function with nodes 1 and 14, you should see something like this drawn to your screen. All right. So if you got something like this, then you are on the right track. If you didn't, no worries. Take a look at the instructor notebook and you'll see a possible implementation available. All right. We're going to have a bit of practice as well using this g.subgraph function as well as the g.neighbors function. So let's combine these guys and say I want to pick a node and I want to draw just that node plus its neighbors. So please give this one a shot as well. Okay, show of thumbs. How many of you are done? Okay, no worries. Let's keep on going for a little bit. As a hint, if you do g.neighbors for a node, the resulting list doesn't include that node. So if you want to, you might want to add back that node to this list so that you can finally do the subgraph function. And if you test it with node number 19, you should get something like this guy over here. Once again, quick show of thumbs. How many of you are done? Okay. Okay, I'm not going to belabor this one too much, but as I mentioned, g.neighbors doesn't return the original thing, so you'd basically have to add back the nodes. You can do g.subgraph of just those guys, or in this case, what I've done here is I've actually manually added back the edges into the graph rather than doing g.subgraph of that list of iterables. But there are many ways to get this one done. All right. But essentially, that's the core idea, right? So I'm going to skip the challenge exercise and leave this as, say, a homework problem if you guys want to try it at home. What I want to do here is revisit this notion of importance in a network, all right? So we've seen nodes that are extremely important as determined by their degree centrality. But you can also say a node is important if I have to pass a message to the network, then that node will show up many, many times in the network, in the message passing problem, right? So essentially, what this allows one to do is to define this metric called Betweenness centrality. So if you take any pair of nodes in the graph and you say how many times, and you ask what is the shortest path that connects these two nodes, you can then interrogate of the nodes that are in the middle, which nodes show up the most, right? And this is defined as the Betweenness centrality. So what I want you guys to do, so you already know, so I've given you here the Betweenness centrality function and how how you're supposed to call on it. What I want you guys to try to do now is to look at, for every node, plot its betweenness centrality against its degree centrality, and take a look at that relationship. So this should be a scatter plot. So how many of you are done with this one? All right, a few hands. Just progressively show your thumb when you're done. In case you wanted to have if you wanted to know what the final scatter plot is supposed to look like, that's what it looks like over there. We're here to look at, in this case, we're not looking at a graph property per se, but we're looking at the relationship between these two centrality metrics. And so first thing you'll notice is degree centrality and betweenness centrality are not perfectly correlated, even though there is somewhat of a correlation between those guys, right? Now, can you think of a reason or a scenario, maybe? Actually, let's do it this way. Can you think of a scenario where a node would have a high betweenness centrality, but would not necessarily have a high degree centrality? Pardon me?
A broker node?
Right. So one example here is a barbell graph. And that's essentially what Paul, right? Paul was saying that it's a broker. This node in the middle over here has two neighbors. But if you wanted to pass a message from this network to the other network, right? A lot of messages would have to go through this broker node over here, right? And that's that is one scenario where the betweenness centrality can be high, but the degree centrality is low. All right? All right, so with this, we are going to end this little notebook section on querying the graph structure with respect to hubs and paths. We're now going to move on to the next notebook, so notebook number 4, which is going to be on cliques, triangles, and squares. So this section on cliques, triangles, and squares is actually an interesting one because it has quite a number of real-world, immediate real-world applications. So for example, if we have a network in which, say it's a social network, in which A knows B and B knows C, is it likely that A also knows C, right? And this is one of those problems of closing triangles. So triangles in a network are essentially comprised of 3 nodes that are connected to one another. And this is the simplest form of a clique in a network. And a clique is defined as a set of nodes for which everybody is connected to everybody else within that set of nodes, right? So if I had 5 nodes, for each individual, there would be 4 edges connecting to every other individual in the network. So this is, say, a motif. This is like an open triangle network motif. So there's this concept of a network motif, which is a recurrent pattern of connectivity that shows up within the graph. And so we've got this open triangle network motif that we can search for in a graph. We can also look for squares, or in this case, it's drawn more like a, I don't know what you call this shape, rectangle. A square is, it's not a clique, all right, but it's got 4 nodes that are connected as you would in drawing a square. And so if we looked at this, it's actually, a square is comprised of 2 open triangles, right? If you think about it. There can be the open triangle ABC. There can be the open triangle, and then the other corresponding open triangle be ADC. Or you could reverse, or you could rotate your frame of reference and make it BCD and DAB, right? So in this section, what we're going to do is we're going to see whether we can identify open triangles and see if we can identify, basically hunt for network motifs is the real idea here, right? So let's start by loading the synthetic network again. Oops, I forgot to run this cell at the top. So what we're going to do first is we're going to try looking for the simplest clique possible, which is the triangle. And we're going to try to look for the triangle network motif inside the social network. So in this case, NetworkX has already implemented an algorithm called nx.triangles, but that only counts the number of triangles that a network is, that a node is present in. It actually doesn't return for you the nodes that are involved in the triangle. So what we're going to try here is we're going to see, we're going to start first with a function that says, is a node present, sorry, actually skip this one, whether it's present in a triangle. We're going to skip over to the exercise below it, which is to get the triangles, get the nodes that that a particular node is in a triangle relationship with it. And so the core idea for finding a triangle relationship is my neighbor's neighbor should include me. So if I have a list of neighbors, and that list of, so my neighbor's neighbor should include me. All right? So if you think through that, can you write a function that extracts all of, so if you're given one node, extract all of the nodes that it's in a triangle relationship with. This is also a fairly challenging problem. So if you want to talk with your neighbors over it, please feel free to do so. So how are people doing with this one? If you test your code, if you're done, test your code with node number 3 and draw that subgraph, and you should see this particular set of nodes coming out. One, two, three, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40. Okay. Show of thumbs, how many of you are done? Okay, we're going to give this more time. This one I'm going to let people try it, let more people try to reach completion on this one, because it's an important, in my opinion, important thing. Okay. Okay, quick show of thumbs. How many of you are done? Okay, let's give it still some more time. And if you're done, maybe look for someone who's not done and see if they need any assistance on this one. Or holler around if you're not done, look for those who are done. That works too. Okay, how are people doing? How many? So I just want to have one more look at thumbs. How many people are done? All right, we've got almost a critical mass. So I'm going to leave it at that for now. It's been about 8 minutes on this problem. If you didn't get it straight away, not to worry, but you can always look back at the implementation in the instructor notebook. This is what a query of node number 3 and its triangle relationship neighbors would look like. And just to prove to you that we didn't indiscriminately look at all of those, if you look down there, there's actually a node number 8 that 3 is not in a triangle relationship with, but it's actually in an open triangle relationship with number 8. All right. So if you look at Facebook's or LinkedIn's, actually LinkedIn was the famous story for this one. When LinkedIn was in its early years, there was this idea that you could maybe connect people who weren't connected on LinkedIn. And the core idea of that problem was to look for open triangles, right? So if A was connected to B and B was connected to C, but in the LinkedIn graph, A was not connected to C, then it was probable that A knew C through B, but they just weren't connected in the graph. Of course, now there's a more sophisticated version of that, which factors in what I was mentioning earlier, homophily, right? Which is people who have similar characteristics or similar attributes are more likely to be connected. So you can factor that into the recommendation of whether two people should be connected or not. But what we're going to do for today is we're going to try to look for the open triangle network motif. So in this following exercise, I would like you to try to look for the open triangle network motif. And the core idea of this motif is if I'm the node for which I want to look for the open triangles, my neighbor on one side and my neighbor on the other side should not be neighbors of each other. Right? Unlike the triangle motif in which my neighbor on one side and my neighbor on the other side should also be neighbors of one another. Right? So try giving this one a shot. And this one is also a little challenging, so if you want to have discussions about the implementation, please feel free to go and try it out.
So we're assuming the input for this function would know that this node is involved in a triangle.
I should clarify that. Yes, make the assumption that it is in an open triangle for now. We can do the error checking later. And if you want an alternate way to formulate the problem, the neighbors of my neighbor on my left side should not overlap with the neighbors of my neighbor on my right side, except for me. So that is also an alternate way of formulating the problem, formulating the solution, sorry.
So they should know the line. So when we had the square, there were no triangles in there because they used
Actually, that's a good point. That's a good point. To the first degree. So from me to them, you're actually right. I think I was wrong. I take back what I say. Let me see. My neighbor on my left and my neighbor on my right, well, basically should not be connected to one another. Yeah, that's right. Yeah, okay, that's right. My neighbor on my left should not include my neighbor on my right as one of their neighbors. That's right. So quick check. How many people are done with this problem? Okay, 1. We'll give this one a bit more time as well. If you're kind of stuck, start talking. Start talking with one another. As a suggested, yes. I'll take a look at that. $25. Actually, I'll suggest that you test it with node number 2. It's a little shorter. And you can actually also, or you can test it with node number 3, which 8 should feature prominently. Yes, that's right. So that's just one suggested output, right? A list of sets. How are people doing on this one? If you're done, okay. If you're feeling stuck, feel free to open up the instructor notebook and inspect that one. Okay, I see thumbs. Any other thumbs? Okay, I see another one. I see another one. Okay, we're getting on track. This was about the expected amount of time that I was thinking as well. This one is a fairly challenging problem. Okay, quick show of thumbs. How many are done with this one? If you raised your thumb once, please raise it again. All right, okay. Let's keep on giving it just a little bit more time. So I'm going to flash up my solution if you guys want to look through it. It's certainly not the most efficient. I never wrote for efficiency in this case. It's probably not the most compact either. But it's just one possible solution. All right. Yes.
That solution has like 7, but I keep getting 8, and I get like 3, 1, 29.
3, 1, 29. So for this guy.
So I think we were just I think we have the same thing, and I was approaching it as treating 3 as the A, and then looking for B and C with C not looking like A. So I think what we're doing is 3 is the B.
I think, yeah, okay. No worries. If you got that one, you were still on the right track, in my opinion. All right, so don't worry about that. The part of the exercise here was to have you try your hand at implementing a network motif searching code, right? So in the previous notebook, Hubs and Paths, we evaluated the importance of certain nodes by looking at the connectivity structure. And in this notebook, we were looking for simple network motifs like triangles, squares, or open triangles, really. And the core idea here is that network motifs essentially are defined by the links in the network. And so if you want to look for network motifs, you can actually decompose your search operations into looking for neighbors and looking for overlapping or differences in sets of neighbors, right? And if you look at the instructor implementation of it, you can get a feel for that. So if you didn't get it this time around, no worries. Don't worry about it. All right, it's totally okay. I just wanted you to take home this idea of how do you implement a search for a network motif, and as well as that, how do you also a more fundamental thing I wanted you to take back was this idea of a network motif that you can search for. It's a recurring pattern in the network. All right? All right, so these were challenging, and I hope you had a bit of fun running through these. The rest of this tutorial is actually going to be a lot more lightweight than what we've had for the past 2.5 hours. All right? So in this next section that I'm going to bring you through, I'm going to show you how you can represent networks in terms of tables. So I'd like everybody to open up notebook number 5. Okay, so if you look at a network, in notebook number 5, we're going to see how we can store network data, we're going to see how we can read network data from tables on disk, all right? So networks, if you think about how NetworkX has implemented it, it's got a node dictionary and it's got an edges dictionary. And essentially, you can store network data in 2 tables. You can store a node table with all the nodes and their node attributes, and you can then also store an edge list, an edge table, in which you have a pair of columns which define the edges, and then you have the rest of the columns defining the edge attributes. All right, so to get a feel for this, I'm going to have you read in this bike sharing data set from Divi. So Divi is in Chicago. I've never been there, but they have a similar bike sharing scheme as in Boston, which uses hub bikes. In 2013, Divi released their bike sharing data set. It was like 700,000 trips released publicly with, of course, anonymized information. And they asked for people to show them how they can visualize this data, and there were a lot of good visualizations. At its core, this data set is a network data set. All right, so I'd like you guys to load it up. Oopsies, what just happened here? Okay, weird stuff. Weird stuff is happening on my notebook. I'm not going to run any more code on my notebook here. What I'd like you to, so I'm just going to use this notebook to take you through what you can do when you're trying to read data from say, CSV files or etc. Now, this is not the only way you can store data. You can also store it in XML files. You can store it else in other structured formats. But this is like one of the easiest ways to, and human readable ways, by the way, for storing network data, all right? So here there is, if you look at the cell below here, there's a node list, and in this case, nodes are stations, all right? And so each station has an ID, it's got a name, it's got a latitude, longitude, etc., a byte capacity parameter as well, and the date it was put online. A lot of them were put online at the same time. If you scroll down, there is a trips CSV file, and these are the trips that were taken from one station to another station. So now you can imagine this is like having a multi-directed graph in which you have the edges are directed, but you're now allowing for multiple edges between nodes. And each edge represents one trip that was taken from one station to the next station. So one thing that might be cool to interrogate is how frequently two stations were traveled between, right? So if two stations are traveled between very often, then that route is probably a very popular route, and there are business implications for Divi. They have to do balancing, load balancing, etc. And so what we can do is we can then ask, how do we construct the graph from this network, from this table, all right? And so just to show you a brief bit of code on this one, you initialize the graph, and you add in the nodes, right? Practically speaking, you would add in the nodes first so that you can add in the node attributes while you're at it. You can then choose to iterate over all of the edges in the edge list. But I caution that for this particular data set because it's 700-something thousand long. And I've tried it, and it takes about 10 minutes or so to load all the data. So Pandas has this nice group by thing, and that was the shortcut hack solution to load in the edges. And in this particular case, we were interested in how many trips were taken between two stations. And if you group by from station and to station ID, simultaneously, you will actually be able to get a length. There will be one resulting data frame that has a particular length. And you can grab the length of that resultant data frame to say that's how many trips were taken. So you can also look for the density of the graph. And so if you looked at the synthetic social network that we were looking at, if you looked at the matrix representation, there were very few ones compared to the entire total number of ones available. That's actually a pretty sparse network. If you look at the Divi data set, then there's actually a lot. So I'm just scrolling through bits and pieces of this notebook here. But if you look through that, there's like a lot of trips that were taken from one station and ending in many, many other stations. And so this graph would be termed, say, a fairly dense graph, right? So there's a lot of, so if you had the matrix representation where there was blue for no edge and red for an edge, in this case there would be a lot of red and very little blue. So that's what one would call a dense graph. Oof. All right. And we can also very quickly, so apply what we learned earlier. We can look at the degree centralities, and you'll notice the scale of the values here has gone really, really small because there are a lot of nodes present inside the graph. And so you can actually then plot the histogram of degree centralities against the node ID, for example, and get a feel for the network. And this is one particular case where I wanted to highlight as well that having a degree centrality that's high doesn't necessarily mean you have a betweenness centrality that is high as well. And if you look through the two histograms that are present inside there, you'll see that. With NetworkX, if you run, if you want to store this to disk, you'll notice we've been using pickled networks. So NetworkX lets you write these graphs to disk so that you can share it with other people. Practically speaking, because in preparation for this tutorial, I had to prepare Python 2.7 versions, and they don't read well in Python 3, so make sure you keep track of your version numbers for that as well. All right? So this was supposed to be one short section on how do you read in tabular data and how do you construct a graph from it. All right? Are there any questions on this stuff? Okay, yes, my apologies. This came up in the rehearsal run as well. So if you could navigate to your directory, there is a divi 2013.zip file. Inside there, you will see inside there you will see the zip file, which you can decompress it. Pardon me? It should have it. So you should see divi stations 2013.csv as well as divi trips 2013.csv. All okay with that? Are there any other questions on this little portion? Okay. So main point here, you can store an edge list as one table, and you can store a node list as another table. All cool? So we're gonna now take a look at the Divi network, and I'm going to give a verbal description of it. There are stations that are really popular. There are routes that are really popular. 2,000 odd trips have been taken between them, or 1,000 odd. I can't remember the exact number. And then there are a lot of stations. There are a lot of routes for which only 1 or 2 trips have been taken between them, right? And this is where we get into this section of statistical thinking on the network. So if a trip is really, really popular, how likely would you expect to see that by pure random chance? Right? Intuitively, we know something that is, if you have trips in which most routes have 10 to 20, right? And now you have a route which has 1,000 trips taken between those 2 nodes. Intuitively, you know that it is probably extremely popular. But how do you prove that, or how do you assess that using a statistical mindset? All right? And so one thing that you can do is you can assume, for example, that the trips are randomly distributed across the routes, and see what that looks like, see what the distribution of trips that are taken looks like across these trips, across the network. All right? Does this make sense? So I know network thinking is already pretty unintuitive. Now we're going to statistical thinking, which is also kind of unintuitive. So if there are any questions, I want to get this cleared out right now. All right, so for this section then, I'd like you to go to Random Networks and Statistics, which is notebook number 6. So if you ran all of the code from the previous notebook, you should end up with a divigraph.pkl inside your Divi 2013 folder, right? Can I just confirm how many people have that? Check your directories. All right, so if you haven't, please run that code. Just run cell, run all, and that should run with no problems, all right? I'm going to unfortunately have to ask those who are running Python 2.7 to not be able, to not take part in the next portion because I have not found the workaround to deal with 2.7. I've been trying to stick with Python 3.4 here throughout this entire tutorial. Yeah, you have to run the previous notebook, notebook number 5. Run it all. Okay. So, right, 759,788 trips. Distributed, if they were distributed randomly across all of the, if they were distributed randomly across the entire network, what would that look like? Right? What would the distribution of number of trips look like? So what we can do is we can actually create this randomized simulation, right? Computation gives us the ability to run simulations, and we're going to do that live here in class. So we can actually run a simulation in which we say, let me pick 2 nodes at random and join them by, and add 1 trip to that counter. If I do it 759,788 times, then I should see what the distribution of trips looks like, trip numbers, sorry, looks like across all of the edges, right? Does that make sense? All right, so how many of you here are on Python 3.4? Please raise your hand. All right, keep them raised. And we're going to, so what we're going to do is we're going to do a manual map reduce. All right, I've tried running this simulation where we go, let's go from 1 to 759,788, and then count, sorry, and then plot the distribution of trip counts. And that actually takes about a few hours. So we're going to do a manual map reduce to make this work out. All right, so if you've got Python 3.4, please raise your hand. All right, I'm going to, you have 3.4 too, Paul? Okay, so you are number 0, and then please continue on snake-like fashion. So 0, 1, 2, next up, 3, 4, 5, any more? Wow, there are still a lot of 2.7 users here. Okay. I mean, I have to use 2.7 because bio packages aren't updated to 3.4. So I understand. All right, so if we took a look, so I actually had a few exercises I wanted to do that, but for those of you who had 3.4, please remember your numbers for the time being, okay? I'd like everybody to now try attempting the 2 exercises that are available in this notebook. So they should be simple calculations. If trips were distributed completely randomly across the network, what would the expected total number of counts be, trip counts be between 2 nodes? Does that make sense, or is it a little fuzzy?
A trip has to originate from 1 node and not arrive at itself. You're not allowing
Self loops. I think self loops are allowed inside here, and they actually show up in the data set. So someone takes a bike, goes shopping, and then comes and returns it to the original station. But so the graph G already has a number of edges that are represented, and self edges are allowed. All right, so if you assumed, so this in statistical thinking actually assumes, we have to make assumptions of what we're talking about. So if you didn't get the exact same answer, no worries. In this case, what I'm saying is the total, because this is a directed graph, we don't divide it by 2. We maintain n square nodes is the total number of possible edges present in the graph. And if we take 760,000 trips and we distribute them randomly across the entire graph, we expect to see about 8.5 trips taken per edge, right? Does this make sense? Right, now if you change the assumptions a little bit, you don't allow self loops, you make it undirected or something like that, then your number will change. The next exercise should also be a quick one. Can you plot a quick histogram of the number of trips taken on each route? So this is use the real data that's present inside this graph G and plot the number of trips that are taken, plot a histogram of the number of trips that are taken. So are people okay with this one? I don't wish to belabor this one for too long either, so I'll just quickly show up my solution. I use the counter and a bar graph rather than a histogram, but really the same idea. All right, and if you use the default histogram, you can't see this thin set of stuff at like 1 to 10 or something like that, and you generally won't see the stuff on the tail side of this side over there as well, because it's like very rare. There's one edge that has like, I don't know, 1,000 plus, 2,000 plus trips taken between them, and there are many edges for which there are very few trips taken. All right? So one other thing you might want to look at is this is a distribution of trip counts. What is the percentile of, what is the percentile, second, 2.5th, 97.5th, and 100th percentile of this distribution? And if you use NumPy's percentile function, you can actually pass in np.percentile, pass in the list of numbers, and then pass in a list of a list of values for which you wish to calculate the percentile. Give this one a quick shot. All right, so if you got this, you were on the right track. And if you didn't, it's totally okay. This required a bit of knowledge of the NumPy API, but that's totally okay. All right, so what we're going to do next is I'm going to have those people who are running Python 3.4 to do the manual map reduce with me, while the rest of you go on to the bipartite graphs section. So what was the highest number that we reached for the number of people with 3.4? 5? Okay. That is going to take quite a while still. So we'll use n equals 40, and we'll do a subsample of the total number of trips. So this won't be representative of the true distribution under where we redistribute all of the trips randomly, but it will give us sort of a feel, all right? So for those of you who are running Python 3.4, please change this number from 40 to, no, leave the number at 40, and then run this cell up here and that cell down there. And finally, write this as a pickle with your ID changed to your number over there. And we will come back to that in a little while. Meanwhile, I want the rest of the class to open up notebook number 7. And notebook number 7 is essentially a very, it's a very short introduction to another type of graph that is slightly different from what we've been looking at. So notebook number, so just want to first confirm, the 3.4 people, are you already running those cells? If you are, hit yes, please. Okay, sounds good. Now and once you're done, please email me your graphs. And I've written code below it that automatically parses through them as long as you've named, as long as you didn't modify the code in the cells, all right? So with this thing about bipartite graphs, this is an interesting and very, in my opinion, still not very well studied field of networks, all right? So what I had earlier on, so my apologies, let me backtrack a little bit. Bipartite graphs are defined as such. You have a set of nodes that belong to one partition, and you have a set of nodes that belong to another partition. You're not allowed to connect nodes that are in the same partition, but you can connect nodes between partitions. And if you look at the Wikipedia entry for bipartite graphs, there's a very clear illustration of how it looks. So earlier on, I had asked you guys to to write a list of cities for which you've been present and explored within the past year. So what I'm going to have you do is within your local group of tables, try to create the bipartite graph of you as individuals and the cities that your physical neighbors have been to, all right? So this means row 1 and row 2 on the left-hand side come together. Row 3 and 4 on the left-hand side come together. And the back row, you're all together. And then on the right-hand side, 1 and 2, and then 3 and 4. So I want you guys talking with one another and actually filling in the code. So the back row is all together. And if you want, you can designate one person to fill in the code. Makes it a little bit more efficient that way. So Python 3 people, are your random simulations done? Have they been sent to me yet? All right. So, almost done. All right. Oh, you had pickle issues? Ah. Okay. Never mind. It's okay. Please email them to me at this email address. And if you are done constructing the bipartite graph, then run the projection of that bipartite graph onto, run the projection. I don't know if I left that code there. I don't think so. But if you fill in this line of code, bipartite.projected graph, and you put B and then you put people, you get the people projection of this bipartite graph, which is the network between people based on their connections with cities. All right, so give that a shot as well. Okay, we'll give this a shot. Let's see. Divi random 1, not PKL. Okay, thank you, Brad. And let's see. Programming, network analysis made simple, data sets, Divi 2013, random 1, ID 2, this is good. Okay, thank you. Thanks, Brad. Thank you, Troy. ericmjl@mit.edu. If it makes more sense to do that, that's totally possible as well. I initially intended 2 rows, but 1 row works too. So how are people doing with the bipartite network? Almost done? Group by group? So in case those who are typing need a bit of example code, this is the one done with me and my wife, right? So we've been to some cities, and there's some cities which we've never been to, but they're also included in this list. So there's this Chinese cities and North American cities, and then I've added a list of edges in which it is person to city, person to city, person to city. And then as you go down, you will notice that there are metrics, centrality metrics that are also available. They're over there.
This one here, did you mean this one here?
Oh, yes, that's right. My bad. Thank you. And finally, if you type in this, once you're done with the bipartite graph construction, run this last line, bipartite.projectedGraph, and then pass in the list of people, and then call on the edges that are available. And with that, I hope to have created some talking points between people who are connected by their cities that they visited. Because part of what we're here for is networking, right? And so, and so I hope this creates a few talking points as you're networking with one another. So how are people doing with that? All cool? Do you all see who's connected to who by their cities? Cities connect people in ways we don't really think are obvious, and people connect cities as well in ways that are probably a little bit more obvious. All right? Okay, so we are at 2 minutes to lunch, and it looks like this piece of code that I wrote, without knowing what the graphs would look like, without knowing what the data, I wrote this off from like pure blankness. Looks like it's taking an unexpectedly long amount of time to run. That's okay. Treat it as my debt to you. I will release the data, the collected pickle networks on GitHub, so that you guys can run this at home as well, if you so choose. All right, and so with that, I want to say some concluding remarks about today's tutorial. So firstly, my hope was that you took back this way of network thinking. It's no longer about the nodes, but the relationships between the nodes. And it's, if you ever elect to go deeper into the network theory world, you'll find that actually the heart of a network is not in the nodes, but it's in the edges, right? The heart of a network is in the edges and not the nodes. And that's a very important point to keep in mind. The second thing I wanted you to take back from this is there are, for free given to you, HivePlot and CircosPlot utilities that we've developed, that I've helped develop for the Python world as part of my own research in grad school. Want to encourage you all to do it, release open source utilities as well as you go along your own work. But these are, more importantly, these are different ways of visualizing the network, and especially HivePlots. It's what Martin, the creator of HivePlots, calls a rational way, rather than looking at hairballs, which are an irrational way of looking at networks. The final part is, I hope you, if you ever need to, you can look at notebook number 5 to refer how to construct networks from tabular data. And finally, as you go home, and if you choose to rerun this notebook, you should be able to see some form of statistical thinking. And I remember seeing the old simulation that I had. The maximum number of trips that were taken was 14, right, on a randomly distributed set of trips. So something that's 1,000 is way out there compared to a random distribution, and therefore we expect it to be of some, well, you could either say it's anomaly, or you don't expect this on a random chance, so something real is happening, all right? So I hope you've taken that back. And with that, I'd like to say thank you for your attention. It's been a wonderful time, and I hope I haven't exhausted you too much with the coding challenges in this tutorial. Thank you very much. The final administrative matter is, could you please go to the GitHub repository and click on the evaluation link at the bottom. PyCon wants to collect this data, so please fill in this evaluation so that they can help evaluate how well we did as instructors.